In the last video, we talked about work, and essentially what we were doing when we were computing the work was we were doing a Riemann sum. A Riemann sum is essentially just the sum of rectangles underneath a curve. So let's say we have a function that looks maybe somewhat parabolic, um, so kind of like an upside down U. Begins at the point A, ends at the point B. And so how we determine the Riemann sum is it's essentially the area underneath a curve according to the sum of rectangles. And in this module, we're going to focus on using the left endpoint only. There are right and left or right hand sums and midpoint sums, and so I want you to think about which one would result in the most accurate estimation for the area underneath this curve. So if I first, well, again, I want to use a rectangle to estimate the area underneath this, but using one rectangle does not result in a good estimate. So maybe I want to make more rectangles, and to do that, I need to divide this interval up into subintervals. So let's say I just have these intervals, and presumably they are all of equal width, which I'm going to call delta x. Okay, so it's delta x from there to there, delta x from here over to here, and so on and so forth. And so if I'm using the left endpoint to approximate the area, or to approximate the area under the curve, what I need to do is for this interval here, this first interval, I'm going to go up to the function and determine where the left endpoint hits the function. And then I'm going to say it's constant over that interval. Okay, so that would be my first rectangle. For my second interval, again, I go to the left endpoint, go up to where it hits the function, and then it's going to be constant over there. So that's going to be the height of my rectangle. Third interval, again, the height of my rectangle is up here, and it's constant over here and down. And just kind of filling these in quickly, I get something that looks like this. And my last one's going to be like that. Okay, so then I add up the area of the rectangles and I'm done. Not too hard geometrically. Now, the idea is, well, how do you can see I'm missing some areas here. So I'm missing like here and here and here, and then I'm overestimating here and here. So how do I get a better estimate? Okay, we're going to talk about that soon. But again, remember, I want to talk about how to obtain this delta x from Euler's method. Remember, we said that the interval width, we just take the difference in the intervals and then divide by the number of subintervals. And this is chosen or chosen by you or specified in the problem. Okay, and so then finally we say the left-hand sum is really just the sum of the different areas. So the width of the rectangle times the height of the rectangle. And so remember that we are using the left endpoint. So actually, b here, the function value at b is never used. Okay, and so again, we said that we want to obtain a better estimate by increasing the number of intervals. So we take a limit and pass the number of subintervals to infinity. This limit is actually called the definite integral from a to b. Okay. Notation-wise, integral, we saw back in Module 4a. A is the lower limit, b is the upper limit, or upper, you can say upper and lower bounds too. And so we're going to discuss how to do this, or do this geometrically, tabularly, and then eventually, when we talk about the fundamental theorem of calculus, we'll actually be able to compute it algebraically. So here, f must be continuous. This is just because otherwise we need to break it up and it gets to be a little ugly. if f is above the x-axis for all x, then the result is just the area between the graph and the x-axis, which we kind of saw back in our example back here. So the function was positive, so the area underneath was just there, or the integral represented the area underneath the curve. Okay, and then lastly is if f is sometimes negative in the interval, then to compute the area geometrically, it's just the area above minus the area below. And this is used for a couple of web work problems too. So for example, if we have this function here, we can just determine where the area is positive, so maybe here and here, and then where the function is below the x-axis. And so what I'm going to do is the area below, which is in red, subtract that from the area that's above, which is in green. And the area above is going to be, well, this is just a triangle, same thing here. So the area for the first part is just going to be 1/2, because it's 1 times 1 times 1/2. And then here it's going to be plus 2. And then we have to subtract this area here. I'm going to do 1 and 1/2 of this triangle and then double it. So it'll be 1 times 1 times 1/2 is 1/2 times 2 is 1. And so my result is just 1.5. So the area or this integral is just equal to 1.5. Okay, not too difficult geometrically. Now here, this function is kind of ugly. So what we're going to do is we're going to estimate the value of this integral from 1 to 6. Okay, so let's go ahead and do this in Excel. Okay, so let's say we want to use 20 subintervals for our first estimate. And again, you should do this with not only 20, but maybe say 30, 40, 50. Remember, increasing the number of intervals increases your estimation, or improves your estimation, sorry, for the integral. So delta x, remember, we have to take the difference in our endpoints, so that's 6 minus 1, and then divide that by the number of subintervals. So we want 20 subintervals. And so I get 1/4 for my delta. So what I need to do is I need to start at 1, and then to this value, to that value, I need to add 0.25 to it, okay, to get the next one. And I'm going to drag this down until I get about 20, until I hit 6. And so I just kind of guessed there, and I ended up at 6. Alright, now remember that I need to know the width of the subinterval, which is our delta x, and I need to know the function value, my left endpoint of that interval, because that's my height. So what I need to do here is I have a function, input these values into the function, so this is equal to 2 to the 0.5 times x. And then I'm going to multiply that by the natural log and just ln. And then I need to do 2 times that number. Close parentheses, enter. Okay, great. And then drag this down to do the computation for me. Okay. Now, since this is the height of my function value, I need to determine the area, so I need to multiply this times my width, which we said was delta x. So I need to take my function value times 0.25. Okay, great, and drag this down. Okay, so I have all these different values, but remember, first of all, that we're only using the left endpoints and not the right endpoints, so I'm actually not going to use these values. I can compute them, but I have to remember that I can't use them, because at 6 that would result in a right endpoint sum. So I would in a right endpoint sum, I would include the values at 6, but here I can't. So I have all the different areas, remember, and now according to the Riemann sum, I just have to add them up. So this is equal to the sum of all these added up, and I get about 36.7. Okay, so right now, if we go back to our notes, we say that this is equal to well, we were saying this is approximately 36.7. And so going back to our notes, we say that this is approximately equal to about 36.7. Um, and again, you should repeat that process in Excel using more intervals to obtain a better estimate. So that's a brief introduction on how to compute the definite integrals tabularly using a table with a complex function, and also graphically by using basic geometric formulas for area.